Okay, thank you. Thank you very much for the introduction. So I'd like to thank the organizers, of course, for organizing this very nice meeting. It's very nice to be able to meet again after all these years of pandemic restrictions. So today I'll tell you about this HIRAX experiment, and in particular, how it can be used to do well, what I think is very interesting, cosmology using H1 or neutral hydrogen intensity mapping. I think it fits very well in the theme of this workshop, large experiments, large surveys, and big data, as you'll see. And a lot of what I'll be presenting, of course, will be results and work from the HIRAX collaboration, in particular, Pascal Hitz was a PhD student at ETH, Devin Crichton also at ETH, a postdoc, and Thierry Vian, who is an engineer at ETH, and Kavim Moodley, who is the PI of the HIRAX experiment at the UKZN University in Durban in South Africa. And of course, many other people have contributed as well. So this is an overview of HIRAX with an artist's conception of the experiment that you see here. The idea is to build an interferometric array, which will comprise up eventually 1,024 radio dishes, each 6 meters in diameters, and which will be operating between 400 and 800 megahertz. You can see some of the parameters of the experiment here. The idea is to build it in stages, which is common for interferometric array. That's one of the advantages. So we'll first build a two dish array, which we call a qualification array, and then an 8 dishes array, 128, 256, and eventually 1,024. The experiment is currently funded all the way to 256, and we're starting to have funding to extend it to the full 1,024. And the idea is to operate the full array for 4 years. I'll be coming back to these different stages when I talk about the schedule. One of the advantages of this experiment is that it will be located on the SARO site close to the SKAO, so using basically all the infrastructure and advantages of being in this Karoo desert and having the infrastructure that the SKO has built for the SK experiment. The dishes are stationary, so it means that they don't move, except that they are tiltable manually from time to time to scan different parts of the sky, as this is a scanning telescope. And the primary driver is a hydrogen intensity mapping, and the experiment will provide a survey of 15,000 square degrees with redshift from 0.8 to 2.5 corresponding to these frequencies. You can see here the field of view, which is about 5-10 degrees. Of course, it depends on frequency, and also the resolution, which is from 0.2 to 0.4 degrees. And that's the target system temperature. So the science goals, well, the primary science goal is intensity mapping with neutral hydrogen, which I'll be focusing on. In particular, the measurement of baryon acoustic oscillation out to this relatively high redshift. Another science goal is to cross-correlate this survey with other cosmological survey in the optical and microwave. I'll come back to that also a little bit later. And then there's other science goals. One is to look for radio transient FRBs, the pulsar searches, neutral hydrogen absorbers, and of course, in the process, whether we like it or not, we'll learn a lot about diffuse galactic polarization and emission in general in these wavelengths. So let me describe H1 intensity mapping. So the idea is to use the 21 centimeter line of hydrogen, which is a hyperfine transition line, to map the distribution, to trace the distribution of neutral hydrogen in the universe, right? And neutral hydrogen traces the large scale structure, so bias tracer, and so we can use it to probe the large scale structure, and from that measure the evolution and properties of the structures as a function of time and scale. Now, the idea of intensity mapping, though, is instead of looking at individual sources, so for example, for H1, sometimes neutral hydrogen is called H1, so I will use both terms interchangeably. So instead of looking at individual galaxies that contain H1 and doing a galaxy survey, the idea is to smooth the H1, the 21 centimeter intensity, and make maps with a lower resolution, and to make, as a result, to consider maps of the neutral hydrogen as opposed to a catalog of H1 containing galaxies. Of course, we can also, because the 21 centimeter line is redshifted, we can get basically a three-dimensional map. So we can get a map for every frequency element, or equivalently for a range of redshifts with very good redshift resolution. So we get a 3D cube. We can also mitigate the galactic foreground, the galactic ones in particular, which are very strong in these wavelengths, by filtering basically the large scales, since these foregrounds are mostly on large scales. Now this will play an increasing important role in cosmology, because if we look back at this famous trumpet diagram, which summarizes the evolution of the universe, what in the last few decades we have in the remarkable progress on making measurement of the cosmic microwave background at high redshift 1100 or so, and also on optical galaxy surveys or near-infrared galaxy surveys, which gives us information around redshift 1 or so. The H1 intensity mapping has the potential to bridge the gap between the CMB and this optical survey by giving us measurement of large-scale structure between redshift 1 and redshift 1100. There's also another way this will bridge the gap is in the sense of the data analysis. You can think of this, the data that this H1 intensity mapping surveys will produce to be somewhere in between the CMB data format and the galaxy survey format, in the sense that it'll be a map, so it'll be in the form of a map on a sphere, like the CMB, but it'll also be three-dimensional, like spectroscopic galaxy surveys as well. And so one has to import methods from both fields in order to learn how to make measurement with very high precision for intensity mapping. So it's also very interesting from the data analysis point of view. So the HIRAX intensity mapping survey will cover, as I said, 15,000 square degrees. You can see the planned region here, which is in the southern sky. As I said, it'll cover redshift between 0.8 and 2.5. And you can see also other overlapping surveys in the region, which is one advantage of doing the survey in the south, in particular DES, KIDS, some CMB experiments, and also the LSST region, which will encompass the entire HIRAX region. So we can also do cross-correlation between the neutral hydrogen and all these different surveys, both in the optical near-infrared and in the cosmic microwave, in the microwave range. So once we know this survey area and the sensitivity, we can make forecasts about the performance of HIRAX for cosmology. You can see this. This is from this paper by Devin Christian, which has given a summary of the experiment. So you see the precision on the measurement of the baryon acoustic oscillation. This is what is plotted is the total power spectrum divided by a smooth version of the power spectrum in which the BAOs were smoothed out. And you see in blue the error bars expected for the HIRAX 256 array, and in, I guess, orange, red, the errors expected for the full 1024 array. And then you can project that into the error on the spherically average distance measure of the baryon acoustic oscillations compared to the one for the Planck lambda CDM model. And you see again the errors. Of course, they go from this 0.8 to about 2.5 square degrees. And you see again in blue the 256 and in red the 1024. And you see the quite high precision that we can get over a wide range of redshift with a single experiment, thanks to the wide redshift, wide frequency range that the experiment will be sensitive to. And then with the Fisher matrix forecast, one can compute the forecasted errors precision on cosmological parameter. In this case, this is the WCDM model. You see the constraints for 256, 1024, together with Planck priors on the WA, W0 parameters, and also on the omega m and sigma 8. Now, what's very important is all the steps that can mitigate the systematic errors as much as possible. So the first one is the choice of the site. As I said, it's quite advantageous that the experiment is co-located with the SKA in the Karoo Desert, which is this region here in South Africa. It's as the name indicates, it's a very underpopulated region, so the radio frequency interference levels are very low. It's also protected by the South African government, and also non-negligibly in terms of logistics, and therefore speed of development as well as cost. We can benefit from the roads, power, and data connection that already exists. And we get access to the southern skies, which gives access to cross-correlation with many surveys. So here is the scheme of the HIRAX instrument here, summarized in this diagram here. So here you see first, the signals are collected by the radio dishes. They're then measured by these feeds. Then the feeds are connected with the RF-OF transmission line to this stage here, which are called iceboard. Sometimes they call the F engine, which digitizes the signal and also separate the signals in different frequency channels. Then the signal from the digital signals from every telescope is then combined together into what we call the X engine or digital correlator, which computes the correlation between the signals and what we call visibilities. And then after that, this information is sent to the next stage, which is a science pre-processing unit, or SDP, which does some pre-processing before the data is sent off-site to large supercomputing centers. Now, one of the challenges is the amount of data that we have to process, and that's why that's a big data experiment, as I was saying before. So just to give you an idea, if we look at the 1024 element array, if we multiply the number of bits per visibility, which is the pair of antenna that are correlated, times the number of pairs of antenna called baselines, times the number of bands in frequency, times the number of samples per day, we get about 150 terabytes per day, or about 220 petabytes for the full 4-year survey. So it's an enormous amount of data. Just as a comparison, this is about 6 times the data rate of the dark energy survey, and about even 7 times the rate for the LSST. So this is a major challenge. And the way we meet the challenge is that a lot of the data processing is done on site with dedicated custom-made computers, basically, both GPU and CPU. So let me tell you a little bit more about this, because it's quite interesting also from the technology point of view. So for example, if we look back at this unit here, which is a digital correlator, what correlates the signals, you can see this digital correlator here. You can see here the rack with multiple nodes. So this is a very dense custom-made GPU system that can process 1.6 terabits per second throughput. This is basically a bunch of very fast NVIDIA GPUs. You can see the inside of each of the nodes. And so this is driven by the development of GPUs for gaming or sort of applications, or machine learning and so on. So we can benefit from that technology. So this was built in Switzerland and is going to be shipped soon into South Africa. That's the next stage. So going back to this is the next stage here. The data rate is still too high to send directly the visibilities from the correlator directly to an external data computing center. So we have to do some pre-processing on site. This is done by the science data processing unit. You see here, it's being built, it's currently being built here. It's next to the correlator. We already have some of the units of this SDP. And that's a complicated diagram, but basically the SDP will have several components that you see here. This is a correlator, that's the data coming from the correlator. Some of them will be used for the FRB, for the pulsar searches, and also for the cosmology intensity mapping survey. And then after all of this processing, it will be sent to first the South African supercomputing center, and then to supercomputing centers in other parts of the world where the collaboration is working. A very important aspect of this is the beam calibration. So in order to mitigate the systematics, in particular the foregrounds, one need to know the beam of the telescope, of the different telescopes very well. So what we'll be doing, and we are actively working on this as well, is combining different techniques, which has different number of advantages together and comparing their performance in terms of calibration. So one of them is this drone calibration. So we are flying drones above the dishes. So we're testing this first at the Blind telescope. There's also work being done at Yale in other telescopes. Blind telescope is a small telescope outside of close to Zurich. So basically we fix the telescope, then we fly the drone above it in some pattern, and then the drone is equipped with a transmitter which acts as an artificial source. And then we scan the region and then reconstruct the beam. This is from this paper here a couple of years ago, where we reconstructed the beam for this Blind telescope. We've now, in the meantime, does many more flights with higher performance, drones in particular. So one of the challenges is the flight duration of these drones. We're comparing that with a technique called holography. So the idea of the holography is to have used the two dishes. So one is fixed, the other one tracks a bright source that moves across the sky. And by correlating the two sources in interferometric mode, one can reconstruct a slice through the beam of the target telescope, which is a fixed telescope. And then we can also reconstruct the beam and compare with the drone measurements. We also recently got funding for doing direct dish metrology on the HIRAX dishes to measure the surface very accurately and the positioning, to build a mechanical model of the dishes. And from that, we can compare to these methods. And we're also working on electromagnetic models. So this is basically a model of the reflectivity of the surface of the dishes, which we can then again compare to the other techniques. So we're comparing all these different techniques. Some of them are easier to deploy. Some of them are faster. Some of them are slower but more accurate. And so we're developing a calibration plan for the experiment. And then we also prepare from the theoretical point of view and simulation point of view. So for that, we need to build a model of the H1 sky, the neutral hydrogen sky. So for that, we use a halo model, and we use a lot of the work that we did that Hamza did over the years, building this halo model. So the halo model has several components. First, it's got the dark matter only components, which is the halo mass function and the halo bias. That gives us the clustering. It gives us a model for the clustering of dark matter halos, and then we paint the neutral hydrogen onto these halos by using a H1 mass to halo relation. You see here the relation in some of these, one of these models for different redshifts. And then we also assume a halo profile, and from that we can measure the clustering of the, we can not measure, we can compute the clustering of the neutral hydrogen in the universe. And then what Hamza did is to fit this model with heuristic functional forms to various data sets with the H1 emission, H1 absorption, also Damblam and alpha. So this model is calibrated on real data. So what then a PhD student at ETH did is that he took this model and then made a simulation realization of the model in 3 dimensions. So in order to do this, he uses a very quick, fast halo simulation using this Pinocchio algorithm, which gives the position in halos and the evolution in 3 dimensions without having to recourse to a full n-body simulation, and then uses this H1 to halo mass relation to paint the H1 onto these halos. And you see an example of 3 of these maps at different correspond to different redshifts or different frequencies. Of course, there's a lot more maps, so I'm just showing 3 here. And then once we have done this, we can test the performance of our, at least forecast the performance of the telescopes. We also have built a HIRAX telescope model. For the moment, we're considering here a simplified version with only 36 dishes, but we'll scale it up to the full array. So we take this input sky map, pass it through this telescope model, derive visibilities, and then pass it through a data analysis pipeline to first reconstruct a map. So you see a map of one of the of a simulated scan of HIRAX on the sky, so the strip here. And then from that map, we can compute the power spectrum, which is showed here in blue. And then in orange, so in blue is the input power spectrum of the input map, and in orange it's the recovered power spectrum from the measured from the simulated measurements. And you see that it agrees quite well on intermediate scale. On small scale, it of course disagrees because we are reaching the resolution of the HIRAX experiment, which is determined by the separation of the largest separation between the dishes, the largest baseline. And then we can also compare it to the analytic halo model that you see in green. So you see good agreement here on large L. The disagreement here on small scale is because here we've been using the Limber approximation, which is not accurate on small scale, especially for a very narrow window function in redshifts. So now we've coded, we're in the process of coding the beyond Limber approximation calculation, and in fact, pretty good agreement. The collaboration status is, as I said, the 256 array is funded through a combination of South African funding, Swiss funding, and also funding from McGill from Canada. And also Canada is also funding some of the dish development. And there's also funding already for an extension of the 256 array. And there's also recent funding from the Simons Foundation, the US, which is now contributing as joined the collaboration. So you see the member universities, South Africa, Europe, and the US and Canada. So the schedule now is accelerating. So it's quite exciting right now. So in the last few months, there was the establishment of a dish factory close to the HIRAX site. You see already the structure which is being built in this factory to eventually produce the molds that will be used to produce the dishes. The next step is in parallel, there's a Clairefontaine testbed site which is close to the final HIRAX site, which is called Swartfontein, which is being prepared. And we will, in September this year, the plan is to commission already a 2-element qualification array. And there we will already test the F engine and a subunit of the correlator as well, see that everything is working together. And then in the beginning of 24, we'll commission 8 elements at the final site and eventually 128 element. And then the following year, we'll build the 256 array. So if you have any question, please look at the HIRAX website, as well as this paper, which is a recent summary of the telescope configuration and also the optimization of the experiment for cosmology. Thank you very much.